All right, in this video we're going to introduce discrete probability distributions, and we'll take a look at creating probability distributions for discrete data types. So a probability distribution is nothing more than a listing of each possible outcome of a probability experiment along with their associated probabilities. And a discrete probability distribution is one in which the outcomes of each experiment are discrete or countable values. And some familiar characteristics from our past discussions on probability is remember that each probability is going to be a value between 0 and 1 inclusive. So we can't have a probability that is negative, and we can't have a probability that is greater than 1. Also, the sum of all the probabilities in a distribution is going to equal 1 because we will account for all possible outcomes in that experiment. So if we add up all the possible outcomes in an experiment, we get 100% or 1. And also our addition rule for mutually exclusive events, that the probability of event A or event B happening is the probability of event A plus the probability of event B. Since these are countable distributions, we don't have to worry about there being a probability of A and B. They will be mutually exclusive. So we can just add the probabilities without having to subtract out where they overlap, because we can't have something happen both 2 and 3 number of times. So mutually exclusive means we just add probabilities together. So here we have the outcomes of rolling 2 dice, where we look at the sum of the pips. So rolling snake eyes, a 1 and a 1, gives us a sum of 2, all the way to rolling 2 sixes, which gives us a sum of 12, and then all the other sums in between. So what we can do is we can look at each of these sums as an outcome of the experiment, so the values from 2 all the way to 12, and then based on the 36 possible outcomes we have in this table, we can create a probability distribution looking at the total number of times 2 comes up, the total number of times 3 comes up, all the way up to and including the total number of times that 12 comes up, all out of 36. So we're going to use the notation P of x equals x, or capital X equals lowercase x, where the capital X is our random variable, and lowercase x represents the outcomes, such as 2, 3, 4, 5, all the way to 12 in this scenario. So this capital X could be our random variable would be the sum of rolling that we get for the 2 dice, and then the sum equaling either 2 or 3 or 4 or the other integers up to and including 12. So don't get too caught up on this notation for right now. All right, so we have 36 outcomes in our table. 6 times 6 is 36. In that 36 outcomes, there's only one possible way we can roll 2, so we have a 1 in 36 chance of rolling a 2. There's 2 out of 36, or 1 out of 18 ways of rolling a 3. 3 out of 36 ways of rolling a 4, which is 1/12, and we just list the rest of them: 1/9 for 5, 5/36 for 6, 1/6 for 7th, and then we're going to notice we get these same fractions going back up for 8 through 12. So the 8 is rolling an 8 is going to be 5 out of 36 as well. 1/9. Rolling a 10 is the same as rolling a 4 for probability purposes. It's 1/12, 1/18, and 1/36. So this is a probability distribution for the sum of the values on 2 dice. So here we have each possible outcome, the sums 2 through 12, along with their associated probabilities, all written in lowest terms. And if we were to add up all these fractions in the second column, we would get 1. As far as a histogram goes, here's what our histogram looks like for rolling our 2 dice. So as you can see, 7 has the highest chances of happening. So if you're looking at what to look for when rolling 2 dice, you have the best chance of getting a 7 compared to everything else. So, all right, example 1, create a probability distribution for flipping a coin 3 times. And this time, capital X is going to represent the number of times heads is flipped, or the number of times we get heads when flipping a coin 3 times. So if we look at the sample space, which the total number of items in the sample space is our denominator, when flipping a coin 3 times, we have a total of 8 possible outcomes from flipping that coin. So chances of flipping no heads, the only time that happens is if we flip 3 tails, which has a 1 out of 8 chance of happening. for flipping heads one time, that could happen when we have heads, tails, tails, or tails, heads, tails, or tails, tails, heads. So getting one time the coin to come up heads would be either heads, tails, tails, that's 1, tails, heads, tails is 2, and tails, tails, heads is 3. So we have 3 out of 8 chance for heads coming up one time. For coming up 2 times, that's heads, heads, tails, there's 1, heads, tails, heads, there's 2, and tails, heads, heads, there's 3. So heads coming up 2 times has the same probability as heads coming up once. Both of them are 3 out of 8. And then the final occurrence where heads comes up all 3 times is this first scenario, heads, 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 which is 1 out of the total 8. And if we take a look, each of these probabilities between 0 and 1, the total is 1 if we add up all these fractions, and the events are mutually exclusive. So the probability of obtaining 1 or 2 heads would be 3/8 plus 3/8, which is 6/8 or 3/4. So part B, create a probability distribution histogram for the number of times heads appear. So it's just taking this table, and the x values here in this first column will be our horizontal axis. The probabilities will be along the vertical axis, and we just create a visual representation, and it looks just like this. So 1/8 is 0.125, and 3/8 is 0.375. So these bars here in the middle are 3 times the size of the bars on the end. So probability histogram for flipping a coin 3 times and counting the number of times heads appears. All right, example 2, the distribution below represents the percentage of households that have X dogs according to a recent study. So households that don't have any dogs, 44% of the households in that study don't have any dogs. 27% of the households in that study have 1 dog, 18% of the households have 2 dogs, and then 11% have 3 or more dogs. So those 11% are really happy because they get all those dogs to play with and have fun with. So how many households have at least 1 dog? So there's a couple ways we could go about doing this. One way is to start, at least 1 means 1 or more. So we could, and since they have to be mutually exclusive here, we could take 27% plus 18%, that's 45%, plus 11% is 56%. We could add up those 3. However, we can also use the complement rule, where the complement of at least 1 is none. So all of the households, 100% minus the 44% that don't have any dogs, gives us again 56% of the households have at least 1 dog living there. So, all right, that about does it for this video. Thanks for watching. I'll see you next time.